Okay, ladies and gentlemen, welcome. Now I'm going to start with the second chapter. Okay. First chapter is quite elementary, but second chapter, I think the second chapter is also elementary a little bit. Okay, so first off, so this will be about stochastic processes. Okay. So number 2. Okay. And what I'm going to do now is going to define stochastic processes here, and I'm going to give you a little characteristics regarding stochastic processes as well. Okay, so what you have here, chapter 2.1. Okay, so this is a subchapter here, the classification. Okay. Okay, so basically I'm going to define it here, what it is. Okay, so what you have here is maybe you remember the definition of the random variable. Okay, so a random variable. Okay, so we had basically omega was a sample space. Okay, and what we also have here is a set which will represent the time. Okay, so this is the time. Okay, usually it is either the set of all integers or the set of real numbers. Okay, so here in this case, so I will add this here. So it is either, so t is equal to z, capital Z, which means that we have the set of all integers, or typically we have the set of real numbers, so either one of the two. Okay? So just representing the time without loss of generality, of course. And of course, if we have a random variable, so that was the first definition, I'm going to give it to you. So random variable. So a random variable was basically, and we're going to write this a little bit differently. So random variable is basically a function, okay, that maps all elements, okay, from the sample space to the set of real numbers. Okay, so this is what the random variable was. We had that already, and now we're going to look at the stochastic processes. Okay, so what is a stochastic process? Okay, I'm going to refer to it as capital Y. Okay, so this is also a function. And what you have is a Cartesian product. You know what the Cartesian product is? Okay, so you have the sample space and the time, and we have the Cartesian product. I'm not sure if whether or not you know what this is. Okay, maybe we're going to look at an example so we forgot what it was. Okay, so we have the Cartesian product. Okay, you can put this in parentheses, but you don't need to. And we map this to the set of real numbers. So that's the only difference. And let me just give you an example. For the Cartesian product, so maybe you don't know what it is. Okay, so this is just what I want to add here. Okay, so suppose that you have the set A. This is going to be the set that consists of the elements 1, 2, and 3. And the set B is going to be the set that consists of the elements 0 and 1. And I'm going to look at the Cartesian product of the two. Okay, so here in this case, this is going to be the set of all pairs. Okay, so the set of all pairs, right? So what you have here is that the first pair would be, the first element has to become, okay, so it has to be something from the set A. So this is always the case, and the second one from the set B. Okay, so here you have 1 and 0, 2 and 0, and and 3 and 0. Okay, so this is the first one. Well, these are the first ones, and the following ones are, okay, so basically the same, right? Okay, except that the second entry is the other entry from the set B. Okay, so here you have 1 from that. Okay, so that is a Cartesian product. So basically, this is the set of ordered pairs. Now, okay, so here, if you want to basically want to know what the Cartesian product of A times or A by T is, okay, so that is the set of all ordered pairs. Okay, so here you have omega and here you have T, for which the property holds that basically you have omega, which is an element of capital omega, okay, denoting the sample space, and of course T as an element of capital T denoting the time. Okay, so this is what the sample space is. Now basically what you have here is, okay, so again, so let me just come back to it. So a stochastic process, as you've seen, okay, in the definition, it is a function that goes from the Cartesian product of the sample space and the time to the set of real numbers. Okay, so this is what you have here. So here you have an assignment here, basically. Okay. So let's say, for instance, if t is fixed, okay, so the time component is fixed. Okay, let's say if t, okay, so t from capital T is fixed, okay, then what you have here is that you assign basically all elements, okay, all elements from the sample space, okay, the elements capital, I call this capital YT, okay, so which is basically a random variable. So this is what you have here is a random variable, okay. All right. So basically, this is a random variable. Okay, so you have a random variable here. Okay, because this is what the random variable does. Okay, so of course, you have that omega is from the sample space here. Okay, I'm going to write this a little bit differently so you see it better. Okay, so basically, what you have here is a random variable. So this is a random variable. Okay, if the sample space is basically fixed, okay, and of course omega here is from the sample space, and that's the first case, right? So if t is fixed, and of course if, let's say, omega is fixed, okay, then you have something else, namely if omega is fixed, then basically what you have is a path. Okay, so here you have a function that maps all elements from capital T, which denotes the time, to the element, I call this capital omega T. Okay, so capital Y of T, and basically, and this is a path. Okay, so basically, here in that case, the randomness is fixed, so you have a certain set of observations regarding the stochastic process. Okay, so this is called the path. Okay, so the path of the stochastic process, and of course, T is from capital T, which denotes time. Okay, so this is what you have in observed process. Okay, now, yeah.
Is the math from T to capital T omega also?
Yes.
It's not T there?
No, this is T.
No,
this is the element. This is the element. So this is a different notation here. Okay. This is different notation for the function. I mean, I'm not sure if you understand this, but let me just consider the following example. So suppose that you have, let's say, the parabola f of x is equal to x squared, right? So maybe it's something that you know, notation. Now this function goes from the set of real numbers to the set of real numbers. Okay, so that's the notation for that. And let's say, for instance, the element 2 is assigned to the element 4, because the square of the element 2 is equal to 4. Okay, so these are the elements here. Okay. Okay, for instance, negative 2 is assigned to be here 4 as well. Okay, you understand? So these are the elements here. Okay.
That means that.
And here, this is the domain, and this is the codomain of the function. So basically here, if you assign certain elements here from omega to this element, then basically what you have here is that you have a function, okay? So you have a function, I'm going to add this here, sorry. Alright, so you have a function that goes from the sample space to, or that maps elements from the sample space to the set of real numbers, so this is the random variable here in this case, right? And here in the other case, you have that this function, okay, so here you have the time, okay, so the time is assigned, I mean, the function goes from the time to the set of real numbers, so you have the path of the stochastic process. This is the function that you have here, okay?
Like omega goes to capital T, omega naturally be T goes to capital T.
No, it doesn't go to capital T, omega goes to the set of real numbers. Okay, so it maps, okay, so the sample space contains all outcomes of a random experiment. So that is fixed now. So for instance, we have the observations today, or whatever. Okay, so randomness is no more existent. So if, let's say, the randomness is fixed, then you have just a function that only depends on time. You understand? So it only depends on time, so therefore you have a path, you have a certain observation. Okay, so this is what the picture, what you see in the lecture notes. Okay, so this is how it looks like. Okay, so here you have, basically, here you have the observations, okay, of the stochastic process. Okay, and here you have the time. Okay, so this is the time axis, and this is how it looks like. Okay, so that's what you see basically. So this is a path. Okay, because there is no more randomness here. Okay, so the observations are there. You don't have like any random event or random experiment anymore. The observations are there. Okay, for instance, stock prices, whatever. Okay, so then you have the path. So in this case, that function that you see here only depends on time. Okay, so that function only depends on time. Therefore, you have actually a function that goes from capital T to a set of real numbers. Okay, these are real numbers here. For instance, whatever, I mean, that might be whatever, 3.12 or something, I don't know, right? So it depends, okay?
In this case, what is fixed? Both?
No, it's the randomness is fixed.
Okay.
So basically, you just have a function that depends on time, okay? So there is no more randomness here. The observations basically are fixed, and the observations depend on time. So if you have that, then you have a path, okay? All right? And if the time is fixed, right? So let's say, okay, we fix the time, then you have a random variable. Okay? That's it. So then you just have a function that only depends on the outcomes of the sample space. So basically a function that depends on the outcome of the sample space is going to be a random variable here in this case. Alright? Okay, so this is just a technical definition, guys.
Yes. If I fix the point in time, I would have a density distribution.
Yes, okay, so that is something that I can illustrate here. So suppose that you have a normally distributed random variable. Okay, so what I do here is, okay, I fix the time here. Alright, so I fix the time. Okay, so let's say we are here somewhere, okay? And we're not sure whether or not, we observe this value or this value. We're not sure, okay? So maybe that could depend on the normal distribution. Okay, so this is a classical picture that you can see here. Okay, so it might be looking like this. Okay, you see this is kind of 3D stuff here. Okay, so you're not sure whether or not, okay, the observation is here or elsewhere. I mean, it depends, right? So suppose that you have a randomly distributed random variable. Okay, so here the time is fixed. Okay, so you have basically a function, all right, that only depends on the outcomes of the sample space. Okay, so here you have a random variable. This is okay, so I mean, you're not sure whether or not the observation will be here or whatever. Okay, so it depends on the randomness. Okay, so you have a random experiment. So here in this case, you have a random variable. Okay, and here you have a function that only depends on time. Okay, so here the time is fixed. Okay, so time is fixed. Okay, so let's say this is equal to whatever t1 or something. Okay, so then you have basically t1 as a fixed time. Okay, right, and then the variable can be anything you like. I mean, it depends on what you observe. Okay, suppose it's normally distributed, then it has like this kind of density function. Okay, so this is what it is about. Okay, but this is just a technical definition, guys. Okay, so basically you have to consider that you have a Cartesian product of the sample space and a set denotes the time. Okay, it's either discrete or continuous. I'm going to come back to it. So this is going to be the next one. Okay, now if let's say the time is fixed, okay, then you have a random variable, and if the randomness is fixed, then you have a path. That's it. Okay, that's it. So randomness fixed meaning that you don't have any randomness anymore. Okay, now this is what it looks like, but this is just a technical definition. Okay, as I said before, okay, so let's say, I'm going to come back to it. So here you have a function, okay, where you have a Cartesian product. Okay, so this is what a stochastic process is again. All right, so if let's say t is equal to the set of all integers, right? So the set of all integers could be, for instance, okay, without loss of generality. Okay, so I have to, okay, so you have the observation points 0, 1, -1, 2, -2, stuff like that, okay? So without loss of generality, of course, okay, without loss of generality. Then, of course, then the stochastic process Y is called and this is why the discrete-time stochastic process. So then Y is a discrete-time stochastic process. Okay, so discrete-time stochastic process. Okay. All right. So basically, I mean, without loss of generality here. Okay. On the other hand, and I told you this before, if the set represents a time is equal to the set of real numbers, okay, the real numbers is basically a union of the set of all irrational numbers and set of rational numbers, okay. So then, of course, then you have that Y is called, or is a continuous time stochastic process, okay. All right. So either you have the set of all integers without loss of generality, or you have the set of real numbers, okay, for the time, depending on what you have. Okay. All right. Now, and on the other hand, so let's say we fix a time. Okay, so we're looking at the values of the random variable. Okay, so basically what you have, this is a stochastic process here. Okay, obviously. And what we do now is we're going to fix the time. So we look at the random variables. Okay, so basically we are looking at the realization. We're looking at the realizations of the random variable. Okay, so basically what you have here is this. Okay, so we're going to fix. Okay, we're going to fix the time. So basically what you have is a function that is only depending on the outcomes of the random experiment. So in that case, what you have here is a random variable, of course. Okay. Okay, so yt is a random variable, and if, let's say, yt, okay, so if yt is discrete, okay, we already know what the discrete random variable is, then the stochastic process is called a discrete-state process. Okay, so then the stochastic process Y is a discrete-state process. Okay. Okay. All right. So this is a discrete-state process. Okay. So there's a discrete-time process and a discrete-state process. I'm going to give you a little example so you can see that later on. Okay. And let's say if the random variable is discrete for all t. Okay. So for all t. Right. So for all time. Okay, and of course, if the random variable, so if, let's say, yt is continuous, okay, then, of course, the stochastic process, okay, so if the random variables that you get, if you fix the time, are continuous for all elements of the time, then the stochastic process is a, of course, continuous state process, okay? Alright? So you have four options, basically. So either you have a discrete time process and a discrete state or a continuous state process, or you have a continuous state process, a continuous time process, sorry, with either a discrete state or a continuous state process. Okay, so there are four categories, if you like. Okay, so let me summarize those because we're gonna see them. Okay, so we have either, okay, so the first category is a discrete time, okay, and discrete state process. this is the first one. Okay, so here of course, so the time is equal to the set of all integers. Okay, so the set of time is equal to the set of all integers, and of course we have that the random variables. Okay, so is discrete. Okay, for all elements here of the time. Okay, so it has to be discrete for all. That's it. Okay, we're not going to look at processes that that change this property in that sense. Okay, so we have so we have a discrete time and discrete state process. Okay, so then we're going to look at the continuous time and discrete state process, right? Okay, so here of course you have that the time is equal to, let's say, time is equal to r, okay, and the random variables are continuous. No, so discrete, sorry, that's it. So we have discrete state process and random variables are still discrete, okay. Okay, of course for all t, that's for certain. Okay, so we don't look basically the stochastic processes that change here in that sense. Okay. Then of course you have a discrete time and continuous state process. Okay, so that's the second one. So we have a discrete time continuous state process. Okay. Obviously. So here in that case you have that t is equal to the set of all integers and yt is continuous. Okay. Okay. For all t, let's say. Okay, so for all points of time. Okay, so no matter what time you take. Okay, so basically you have a continuous random variable. And let's say then the last one is of course a continuous time and continuous state process. Okay. Okay, so this is going to be it. Can you read this? Okay. So if not, then I will read this for you. Okay. So the first one is a discrete time and discrete state process. The second one is a continuous time and discrete state process. The third one is a discrete time and continuous state process. And the last one is a continuous time and a continuous state process. Now here for a continuous time and a continuous state process, you have that basically, okay, so that the set representing the time is equal to the set of real numbers, and yt is continuous, of course. Okay. For all points of time. Okay, so basically we're not gonna distinguish. Okay, so here, okay, so let me just demonstrate that for you. Okay, so how this might look like. Okay, so for instance, let's start with a continuous time and a continuous state process. Okay, so basically let's say, okay, so this is the first one, or the last one in this list. Okay, but this is the easiest. Okay, continuous time and continuous state process. Okay, so basically that was the first picture. Okay, so that you were getting. So here you have the time. Okay, here you're going to have the process itself. Okay, so let's say the process looks like this, maybe. Okay, so there are no interruptions, nothing. Okay, and for all observation points, which are denoting the fixed points of time. Okay, so there is basically the possibility that. Okay, so you have, let's say, a continuous density, for instance. Okay, so here at this point you have this observation point, okay? So it could be, for instance, here, okay? So these are the possibilities, okay? So I represent here, I use the normal density here, guys, okay? So this is the normal density, okay? And that you have that for all observation points, basically, okay? Could be somewhere up there. I mean, it doesn't have to be necessarily in the middle, okay? So it could be anywhere you like, okay? Can even change the shape of the form, whatever. Okay, so these lines, basically already represent density functions. Okay, so these are possible outcomes, let's say. And if you have the normal density, then of course you have a continuous random variable. Okay, so this is okay. So there are no interruptions here. Okay, and basically you have the possibility for that. Now, if let's say the time is interrupted in that sense, okay, so and everything else is the same, then you have basically a discrete time in a continuous state process. Okay, so this is going to be the second one. So this is going to be a discrete time and continuous state process. Okay. So this looks like, okay, as follows. Okay, so basically it would be more or less the same. Let's say it's more or less the same as the previous one. Okay, but you have like these kind of interruptions. Okay, so for these observation points, okay, so there are these kind of interruptions. Okay, so I try to stick to the previous example. I'm not sure whether or not it. Okay, so it is possible. Okay, and here for all observation points, okay, you have, let's say, for instance, normal density. Okay, so there is always the possibility for the stochastic process to be something else. Okay, which basically can relate to, for instance, the normal density. I mean, it's not necessarily the normal density, but that's the most common one. So maybe this is something that you'll see more of, most often. Okay, so this is a discrete time and a continuous state process. Again, we assume that these interruptions here occur at points of time 0, 1, 2, 3, 4, 5, 6, 7, blah blah blah, but it doesn't matter. Basically, it could be also something else. All right. So this is just for you, just to the illustration. Okay. Okay. So here you have the normal densities representing the possible outcomes of, let's say, a certain element. Okay. Okay. So here I have a discrete time and a continuous state process. Okay. Basically. Okay. And now we're gonna look at the continuous time and discrete state process. Continuous time and discrete state process. Okay. Example of that would be, for instance, something like this. Okay. So just you have basically so a continuous time and discrete state process. So for instance, something like that. Okay. So if you have observations like these, okay, right? So is that what you observe? Okay, it could be also somewhere else. I mean, they're not necessarily equal distance, but you have just continuous time and discrete state process. Okay, and the last one, namely the discrete time and discrete state process, is just it's the same thing as here, but having just the time being interrupted. Okay, let's say at certain points. Okay. So let's say continuous time and discrete state process is blue, and a discrete time, okay, a discrete time and discrete state process, okay, is represented, okay, let's say by these dots here. Okay, so you have these dots, let's say, okay. All right, so just these kind of interruptions, so only at a certain points of time, okay, right? So that's the last one. Okay, this is how it will look like. Again, but this is just a representation, guys. We're supposed to understand basically what we're talking about. Now we're going to talk about here in this setup, we're going to talk about the discrete time continuous state process. This is what we're going to look at. Okay, so in time series analysis, we're going to look at the discrete time continuous state process. Okay? Okay, so we have just a certain points of time, maybe 0, 1, 2, 3, 4, 5. Okay, so this is what we're going to look at. Alright? And we have basically, we can basically, assume that the random variable, okay, which relates to the stochastic process is of course a continuous one. Okay? Basically, but usually even though you have a discrete time and a continuous state process, okay, so this is what you're going to look at, you probably have seen this, and I have this also in lecture notes, that you still connect the points, okay? but this is just a representation. Usually, usually you wouldn't, okay? So because let's say you have day 1, day 2, day 3, and stuff like that, you have nothing in between, okay? So if let's say you have the observation just at the end of the day, okay, you don't have, let's say, anything, whatever, in the afternoon or something like that, okay? So you don't have observation, but still people, you know, are connecting these points, whatever the reason that might be, okay? All right, so just be aware of that, okay? Now, that's basically it. So this is basically the definition, okay? So you're supposed to know what a stochastic process is, okay? How this relates to a random variable. What is a path, okay? So what is a path of a stochastic process? Here, in this case, we have all just paths because we fixed the randomness here, all right? And you're supposed to know, you know, these 4 categories, what they are, basically, okay? So discrete-time and a continuous time stochastic process versus a discrete-state and a continuous state process, okay? So this is quite elementary as well, but you should be aware of that. Now the second subchapter here of this is going to be the stationarity, okay? So this is basically what is a little bit more important than that, okay? So you know what the covariance of, let's say, of two processes are, okay? And let's say we have a stochastic process, okay? So why is it a stochastic process, okay? And now we fix the time, okay? Basically. So you have random variables, right? Okay, so this is yt is a random variable, okay? Because the time is fixed, all right? So the time is fixed, basically. And what you can do is, you have seen this, you could consider, for instance, the covariance of the random variable yt and the random variable yt plus h, okay? So when h is a certain number, okay, so you have basically the covariance at a certain point of time, okay, or random variable at a certain point of time, and another random variable at another point of time, okay, so basically, okay, so where, of course, h is not equal 0 here in this sense, okay, so this is the covariance of the random variable, okay, with respect to h, and the covariance of that is called the autocovariance here in this sense. Okay, so this is the autocovariance, guys. Okay, so basically, you know what the definition of the covariance is. You have seen this, so but I will denote this here anyway. So you have the covariance of the two.
Can h
Yes.
be negative?
Yes, it can be negative too. Okay, so if you look at the past, okay, it can be negative. But the thing is this, if you, let's say, if t is equal to 0 and you look at the past, then you don't have the randomness anymore. So then basically these values are fixed, okay? So h can be negative, of course, but it depends whether or not it makes sense, okay? So because you're not supposed to be in the past, again, if you're in the past, you don't have the randomness anymore, okay? So basically the covariance, there is no variance here of the variable, so this will be just a constant, which is of course 0. But we're not going to look at that case, all right? Okay, so here, the definition, you have seen this, okay? So this is the expectation of the product, okay? So this is the most common one that I used here. So this expectation of the product of the two, all right, minus the product of the expectations, okay? Again, but this is just an application. Now, we say autocovariance is just a covariance, okay? So from now on, I will use the term autocovariance instead of the covariance, but basically what I mean is that's just a covariance, okay? All right? All right? Now, if let's say the autocovariance, okay, the autocovariance of these, okay, is basically not equal to 0, okay? So then what you have is that the process is called autocorrelated or serially correlated. Okay, so if the autocovariance is not 0, then the process, okay, so then Y is called autocorrelated, okay? Okay, so it's either autocorrelated, you can say it's autocorrelated, so basically you say basically the process is autocorrelated, okay, so there is a linear relationship between, each random variable of which the process consists of, okay? Or you can say it's serially correlated, okay? So this is basically both correct, okay? So serial correlation, okay, and autocorrelation are the same thing, okay? All right. Okay. So if the covariance is equal to 0, then there is no serial correlation in the process. Okay? So there is no relationship between, let's say, the current observation and the observation of the past. Okay? Or a current observation and the observation of the future. Okay? Assuming that you didn't observe the process, right? Alright? So this is what it means basically. So there is no relationship. Okay, so if that's the case, right, so then the observation that you're going to have in the future, okay, and there is no linear relationship of the observation that you're going to have in the future and the observation that you have today, right? Excuse me, you wanted to ask something?
No.
Yeah, okay. Alright. Now that does not mean that the process is not independent, okay? So just because there is no linear relationship, it doesn't mean that that there is no relationship at all. So just because a process is not serially correlated, it doesn't mean that this cannot be independent, of course. Okay. Now, and basically, this is the autocovariance, and of course, we can also define the autocorrelation as well. Okay. So basically, what you have, you remember the correlation, right? So the correlation of let's say two random variables. Okay, which are basically here in this case are drawn from the stochastic process, and this is going to be, of course, the autocovariance of the two, all right, divided by basically the standard deviations. Okay, so the standard deviation of the random variable, in this case yt, and the standard deviation of the random variable yt plus h. Now that is called, okay, so this is called the, of course, autocorrelation. Okay, so ρ is the autocorrelation. Okay, so instead of the covariance, you say the autocovariance in terms of the time series, and instead of correlation, you basically say the autocorrelation. But it's not wrong if you say correlation. Okay, right? It should be fine, but it's more like, the professional term, right? So then basically you are someone, if you say autocorrelation, then you're signaling to your audience that you have heard of time series, maybe, okay, which is a good thing. Now, okay, just for you to know. All right, now what I'm going to do here is I'm going to define a stationary process. Okay, so what is a stationary process? And this is what you're going to look at. Okay. So this is the next definition. Okay, so the stochastic process, I'm going to call this just capital Y, okay, because it's just a stochastic process it refers to, is called stationary. Okay. And I have to admit, we only look at the stationary here in the weak sense. Okay, so this is basically so-called weak sense stationary. Okay, but this is something that you might consider. Okay, so in the stationarity in the weak sense. Okay, so this is a so-called weak sense stationarity. Okay. Because the other one is that might be too theoretical, so we're not going to consider that. We just consider the so-called weak sense stationarity, and I use just the word stationarity instead. So if I say stationary, okay, so if I say, let's say the process is stationary, then I basically mean that it's stationary from the weak sense point of view. Okay. Now, if let's say the following properties are satisfied, and all properties supposed to be satisfied, and there are 3 of them. Okay, so I'm going to collect those. Okay, so each and every one of them has to be satisfied. Okay. Now basically it means, okay, so it basically means that the mean of the process, okay, that the mean of the process, first off, is finite. Okay, so the mean is finite. Okay, so that means that it's less than okay, less than infinity. Okay, so the mean is not infinite, first off. Okay, and the second property is that the mean does not depend on time. Okay, so this thing here does not depend on time. Okay, so basically on t, right? So does not depend on time. Okay, for any of the case. So basically that means that the mean is constant, guys, and finite. Okay, so the mean is constant all the time. Okay, so basically, I mean, sometimes the process is like, you know, sometimes it's larger than its mean, sometimes it's less than its mean. Okay, but over time, it's basically the mean is constant. I'm going to just give you a picture how does it look like, you know, so when you recognize let's say a stationary process. Now, the second property is that, okay, so this is the time independence of the mean, right? So the mean does not depend on time, and it's finite. And the second thing here is that it's also supposed to be true for the variance as well. Okay, so the variance, okay, would also satisfy the same conditions. Namely, the variance is finite, okay, right, at all times. Okay, so there is no such thing as the infinite variance, okay, because if that was the case, you know, the process would literally explode. Okay, so I mean, of course, if the variance is not finite, it does not depend on time. Okay, so you have to be a little bit careful. Just because let's say a moment here that does not depend on time, okay, it's still not necessary for the process to be stationary because it has to be finite. So if it's not finite, then it also does not depend on time. So not depending on time is not sufficient, but basically, I mean, basically it's the condition that, you know, that the mean, of course, is finite is basically limited. Okay, so the variance is also finite here, and the variance does not depend on time either. Okay, so the variance should not depend on time. Okay. Okay. All right. And the third one is, of course, the covariance. Okay, so basically, and or the autocorrelation, let's say. Okay, so you have the autocovariance. Okay, and the autocovariance is also finite. Okay, so that has to be also finite, and it doesn't depend on t either. Okay, so it doesn't depend on t basically. Okay. Okay, so that does not, okay, so, and the autocovariance, okay, does not depend, okay, does not depend on time, on t, okay, but it can depend on h, okay, so h basically is called the time lag, okay, so h is a time lag, okay, so I've used parentheses to note this, okay, but it can depend on the time lag, right? It can depend on h, right? So basically, it means that the process, okay, can be serially correlated, okay? It can be serially correlated, okay, but it's not necessarily the case. And a serial correlation only depends on the time distance between the sampling points, but not the concrete time of the sampling point itself. Okay? So let's say the autocorrelation at between point 10 and point 12 is going to be the same as the autocorrelation between point 20 and 22. You understand? Okay, so that only depends on the time distance. That can be the case, but it's not necessarily the case. Okay? All right? Okay, now how does it look like, for instance? How would you recognize it? So as a process, okay, which is stationary. And this is what we have here. Okay? Okay, so how does it look like? I mean, you're supposed to be aware or recognize maybe how does a stationary stochastic process look like? I mean, okay, so you see in the lecture notes, okay, so basically, no, I try to be a little bit better than this, okay. All right, maybe something like that, okay. So basically what you have here is that the mean is constant, okay, so this is the mean. And the mean does not depend on time, right? And of course, you also have that the variance or the variation of the process, okay, does not depend on time either. Okay, so basically, you have the same variation all the time. Okay, so this is, I mean, this would, you know, typical stationary process. Okay, so this is a stationary process, right? Okay. I always look in the diagram before I analyze data. I always look in the diagram as I would see, figure out, I mean, whether or not it could be stationary or not. So sometimes you would see this in the diagram. So, okay. Now, how does that say, for instance, let's say, suppose that the variance is constant, but there is a time dependency of the mean. Now, how would a time dependency of the mean would look like, for instance? Okay. So here, in this case. So what I'm going to do here is I'm going to give you an example how, let's say, for instance, a time-dependent mean would look like. So for instance, of course, it's quite obvious that here the mean does not depend on time, but it could be something like this, for instance, okay? So here, okay, so let's say, for instance, you have a linear mean, okay? So that's the mean of the process, right? And the process just evolves around that, okay? Alright, you see? So this is what I mean here. Well, basically, okay, so basically the variation around that mean, okay, is constant. Okay, so you have basically that the mean at the process is, or the mean of the process is time dependent, okay? Mean is time dependent, okay? Okay. Okay. But the variance is constant. Okay. So the variance is constant. Okay. More or less. Right. Well, this is just symbolically, I mean, of course. Right. Okay. So here the variance is constant, but the mean is time dependent. All right. So that could be, for instance, a linear trend in the data. If you have a linear trend in the data, then the data is not stationary, period. Okay? Okay, it could be stationary around that mean. Okay, so if you eliminate the mean, it probably could be that the data will become stationary, but this is what we're going to look at. And since the mean is time dependent, okay, so it could be, for instance, a linear function, then you no longer have a stationary process. So this is not a stationary process, guys. Okay? All right? Now, for instance, what happens if you have a time dependency in the variance, but not a time dependency in the mean? So suppose that you have a mean that is not time dependent. Okay, so this is the mean again, but you have a time dependency in the variance. Okay, so that could look like this. So, for instance, suppose it could look like this. So here you have basically a time period where the variance is like this large, and then you have, let's say, a time period for which, you know, the variances become larger and then become smaller again, right? You see? So here in this case, I mean, you have a constant mean, so the mean is not time dependent, but the variance is, okay? So here, basically the variance changes, right? So the variation of the process changes over time. Okay, so here you have a time dependent variance, okay? understand? So basically then you no longer have a stationary process still, okay? Because the variance is probably depending on time, so what you basically have is, so here between these two observation points, the variance tends to be a little bit larger than is usual, okay? Alright, so that could be an example for that. So then you don't have a stationary process either, okay? Now there are tests regarding this, so you can test whether or not the process is stationary, okay? So, but we will learn that, of course, but of course we have to know, I mean, first we're supposed to recognize what it means and stuff like that, okay? Alright? You understand this? Okay? Now it could be very difficult, relatively difficult to say you have let's say a process which is time dependent, it's not time dependent for the mean, and its variance is also not time dependent either, but let's say the covariance is time dependent. Now that is something that you might not recognize here from the data at the first side. So time dependent covariance is relatively difficult to, basically just difficult to analyze. Okay. Now maybe we can just skip that here. Now there are basic properties, okay, that these things satisfy. Okay, so for instance, the first property that the autocorrelation satisfy is that, let's say, if the process is stationary, so if y is stationary, okay, then basically the autocorrelation only depends on the time lag. Okay, so then the autocorrelation okay, so the autocorrelation, which is basically what I'm talking about, this expression here, okay, only depends on h, okay, which is a time lag. Alright, see? I mean, we had that. It doesn't depend on t, but it only depends on h. Okay. Alright? If, let's say, even, right? So if that is, let's say, autocorrelation in the process, then the autocorrelation only depends on the time lag. Okay? Alright? Okay? Now, in this case, since this is the case, in this case we denote the autocorrelation as follows. Okay, so in this case, okay, alright. Okay, we have that basically that the autocorrelation, okay, this is just the same thing, only depends on the time lag. So basically you have, I use a different notation. So I say this is rho of the process y, just depending on h.